So today we have Dr. Caroline Ghorayeb, who is the Margaret Burbridge Prize Postdoctoral Fellow at University of Chicago. She got her PhD in 2024 from University of Montreal for studying formation, composition, and evolution of atmospheres of small exoplanets. And that, of course, is also the topic of our talk today. And during her PhD, she received the Jorge Beryl Prize for Academic Excellence. I'm sorry if I'm mispronouncing that name. And DAWG Student Scholarship. So yeah, it's great to have her with us today. And Caroline, whenever you're ready, we can begin with your talk.
Okay, yeah, awesome. Thank you for the introduction. So I'm Caroline-Ghorayeb. I'm a postdoc at the University of Chicago. And today I'll be talking to you about exoplanets, planets outside of the solar system. And in particular, I hope that you leave thinking a little bit more broadly about where we're at in terms of the search for habitability, habitable conditions, on small exoplanets, as well as figuring out some of the things that we're now able to do technologically using telescopes such as JWST, the James Webb Space Telescope. So because I didn't know exactly the background of everyone attending, I'm going to start with an introduction of kind of what we've learned about small exoplanets in the past decade or so. And a lot of this has come from what we call the transit method. So for most exoplanets, we can't observe them directly. And instead, we infer their presence via what we call the transit method. So essentially, we monitor the light that we receive from a lot of different stars. And if planets orbit these stars in such a way that they periodically occult the surface of the star from our point of view, we're going to see a periodic dimming in the light from these specific stars. And the amount of dimming that's going on essentially will inform us about the planet's size. So because this is essentially the easiest property to measure for an exoplanet, this is the one that we have the most data for. And so this is what was used to initially inform our understanding of the diversity of planets and more specifically of small exoplanets. So what you're looking at here is a histogram showing the amount of planets that have been discovered as a function of planet size. And to inform this a little more, I'll add some cartoons showing where the planets in the solar system would lie. So just as a pointer, the Earth is the largest rocky planet or terrestrial planet in the solar system, while Neptune is the smallest of the gas giant population. And what you can see is that actually the vast majority of exoplanets we've discovered so far have sizes intermediate between the Earth and Neptune. And that has sparked a lot of interest and a lot of surprise in the exoplanet field because all of our models of the formation and evolution of planetary systems, which were initially based on the solar system, of course, didn't predict the existence of any of those planets. So in the field and more generally throughout this talk, I will be referring to planets of the size of the Earth or a little bit smaller as sub-Earth. And for the planets that are intermediate between the Earth and Neptune, we kind of have this denomination that this first peak in occurrence rate, planets a little bit larger than the Earth, which are all often thought of as rocky scaled up version of the Earth, we'll call super-Earth. While the slightly larger ones, but still smaller than Neptunes, are perhaps not very creatively called sub-Neptunes. And this essentially encapsulates our complete lack of understanding of the compositions of these planets. Sub-Neptunes in particular have low densities that tell us that they can't just be rocky. They need to have a gas envelope. But the question of whether they are just scaled down versions of Neptune with hydrogen-rich envelope and perhaps a lot of volatile species like water or methane in their interior, or whether their nature is completely different, is still a big question in the field. And this is also important for the habitability question, because as we're initially thinking of this as searching for twins of the Earth, kind of Earth 2.0s, and with the smaller planet size in mind, there's also this whole host of planets to mind that are a little bit larger than the Earth and perhaps could have these exotic compositions that may still allow for liquid water to form. So this is essentially the breadth of what I'll be covering today. Beyond planet sizes, one of the main goals of exoplanet science today, and especially in the era of JWST, is to understand planetary and atmospheric compositions. And for this, the main method that we use is called transmission spectroscopy. So it's essentially the same as the transit method that I was describing earlier. But instead of simply measuring the size of the planets, the amount of total dimming that it causes to the light from the star, we account for the fact that the star's light is not just going to be blocked by the core of the planet, but it is also going to interact with any molecules that are present in the planet's atmosphere. And each of these molecules will interact differently with different wavelengths of light. And this is what is illustrated here. What you're looking at is the signatures or the amount of absorption that you expect from different molecules in the different colors as a function of wavelength, with the full wavelength range here covering everything that JWST can look at. And what you can see is that each molecule has kind of these very specific fingerprints where it's absorbing at certain wavelengths than others. And so if we observe precise transmission spectra, so is there an issue, a technical issue? I'm seeing movement in the room.
Yeah, I'm trying to see if I can make the screen larger. Can you give me just a few seconds?
Yeah, of course. Just give me a heads up when everything's okay.
Okay, great. Does anyone know how to switch off these lights?
Sorry?
No, sorry, I'm asking people here.
I think it's the light switches like right beside you.
This is better. What do you switch on these ones?
Yes. Yeah.
Okay, let's go back to this. Yeah, let's get rid of this manually. I think people, I mean, they're okay with the slide size. All right, I think we can continue. Thank you.
Okay. Let me know, give me a heads up or just wave or something so I can see
Yeah.
in the Zoom if there's further technical issues on your end.
Thanks.
Yeah, so I was talking specifically here about the fact that by measuring the depth of a planet's transit at different wavelengths, we can actually decipher which molecules are present in its atmosphere and in what amount. And that's one of the main goals of what we're doing with the JWST. And so as we think now in the context of habitability, one of the questions that one could ask is on which planets is water even present? And then the second question of where liquid water conditions would be met. For that second context, usually the first thing we think about is temperature. So we want a planet that's not too close or too far from its host star such that it could have liquid water at its surface. This is what we call the habitable zone. That's highlighted here in green. But even before we think about liquid water, for water to be liquid at the surface of a planet, we need to have an atmospheric pressure that actually allows that to happen. And this requires knowing whether a rocky exoplanet has whether it has an atmosphere, essentially, that could sustain liquid water. Now, again, if we expand this vision a little more to even larger planets, such as sub-Neptunes, there could be exotic compositions that allow for the presence of liquid water, even in atmospheres that are vastly different from the Earth. And so I'll address that a little later in the talk. But first, if we focus on, let's say, the canonical temperate exo-Earth rocky planet, our biggest question remains, which of those planets actually have atmospheres? Before talking about any specific exoplanet, I wanted to give you a little tour of the rocky planet atmospheres that we know about. In the solar system, we have the very thin atmosphere of Mars that's very rich in CO2. We have Earth's atmosphere that's much thicker, but is there dominated by nitrogen and oxygen. And then we have Venus that's much cloudier, but has a very thick atmosphere, again, dominated by carbon dioxide. If we look more broadly to moons, Titan also has a very interesting atmosphere in that it's about as thick as the atmosphere of the Earth, but there it has a very different composition where instead of having a lot of oxygen, it instead is very rich in methane. So we can already see this huge diversity just here in the solar system around this one star, the sun. But now the question is, which of the ton of rocky exoplanets that we know about actually have atmospheres, and what do these atmospheres look like? In the solar system, a lot of the atmospheres that I mentioned aren't very suitable for life. The biggest barrier there has been that to predict theoretically whether or not a planet has an atmosphere, our theory depends on factors that observations essentially can't provide because they hinge on the history of the planetary system, such as how much X-ray and UV irradiation the planet has received that could blow away its atmosphere, or even how many volatiles, how much water the planet initially started out with, to see whether or not this reservoir could be depleted today. And so instead, us as observers have taken this opposite approach of looking to atmospheric reconnaissance, essentially figuring out for individual planets whether or not we detect or don't detect an atmosphere, and kind of backtracking from that, where in planetary systems, when in the history of the system, and perhaps for how long, small rocky planets could either hold on to their initial atmospheres or revive them through things like volcanism, for instance. This is one of the main focus of the field right now. There is a 500-hour, which is one of the biggest programs on the JWST, Director's Discretionary Time Program, that's focused on delineating what we call this cosmic shoreline, essentially the range of planetary gravities and amount of insulations that a planet can receive where it could be able to retain an atmosphere. So based on that is, again, the same approach of studying a specific exoplanet, figuring out whether or not it has an atmosphere, and kind of adding that as a data point in our understanding to figure out if there's a part of the parameter space that could be carved out where we actually find rocky planets with atmospheres. Another system, a specific system that has actually received a lot of attention is the TRAPPIST-1 system. So you might have heard about it. And what makes it so interesting is that TRAPPIST-1 is an extremely small star. It's just a little bit larger than Jupiter in our own solar system. And we generally like this to study small exoplanets because you can imagine that if we study transits, well, the amount of light that will be blocked by even a small planet, if it orbits a very small star, is going to be enormous. So this is a very easy signal to detect. And that also means that it makes it easier to search for even thin atmospheres, like the atmosphere of the Earth, which is much thinner than the atmospheres of giant exoplanets that we're much more used to studying. The other thing that's very exciting about TRAPPIST-1 in particular is that it is orbited by at least 7 small rocky exoplanets. And so just this system has been the focus of over 400 hours of JWST observations. what makes this interesting in the context of understanding broadly which rocky exoplanets actually have atmospheres is that because we have 7 test planets around the same star, a lot of the factors that we don't know about are actually shared across the different planets. And the individual differences that we could find between one planet and the other will be just differences in its mass and gravity or the amount of irradiation that it received, for instance. And the interesting thing about this is that it means we can play a game of multiple birds with one stone, meaning if we study a planet that's kind of in the middle of the system, let's say TRAPPIST-1e, and we find it doesn't have an atmosphere, well, then that updates our understanding of the likelihood of atmosphere presence on all of the TRAPPIST-1 planets. There have been studies so far of the innermost TRAPPIST-1 planets and some tentative studies of planets a little bit further out, but the main takeaway is that no atmospheric signatures have been detected. What you can see as the measurements here are the measurements of the depth of the transit I was talking about before as a function of wavelength. And so if there were molecules present, you would really expect them to have huge variations as a function of wavelength, but you're seeing something that looks very flat that tells you that at least it doesn't have a very thick atmosphere. But for the innermost TRAPPIST-1 planets, that doesn't necessarily help us much with playing this game of 2 birds with 1 stone, because they were so close to the host star, and TRAPPIST-1 is such an active star that we wouldn't necessarily expect these planets to have atmospheres to begin with. And so that's where my study and our team's study of TRAPPIST-1d was really exciting, because we're really entering this realm of what we call high reward atmospheric reconnaissance, essentially studying planets where we know that whether or not this planet has an atmosphere will actually impact how we think about the entire system. TRAPPIST-1d is actually a very small planet. It's only 80% of the size of the Earth, 40% of its mass, and it receives a little bit more irradiation than the Earth. So models predict that, some models predict it could have liquid water. Some models predict that all water would be in the atmosphere, which we're still kind of going into this regime towards habitable exoplanets. And there, from a theoretical standpoint, the odds of it having completely lost its atmosphere today were at about 50-50, which means that whether we find an atmosphere or we don't, we're still learning something very valuable. And so as part of the NEED's Guaranteed Time Observations program, we obtained 2 transits of TRAPPIST-1d with NIRSPEC PRISM, which is the instrument on the JWST that has this widest near-infrared wavelength coverage, really enabling us to search for all sorts of even exotic compositions. And what you're seeing here is the transmission spectrum that we measure. So to the best of our understanding, again here, you're looking at something that looks very much like a flat line. And so what I want you to focus on, and what has been kind of what the community has been trying to think about, is what do those error bars mean? We know that what we observe doesn't match a thick atmosphere that would be rich in lighter species like hydrogen and helium. That's the model that you would see in brown in the background here. But we're really getting to this regime of precision where we could find even very thin atmospheres, like the atmosphere of the Earth, that would be only 1 bar of surface pressure compared to kind of the hundreds or thousands of bars of the giant planet atmospheres. And so all these different colored lines that you're seeing in the background that kind of all fall within this realm of possibility, all are for Earth-like, in terms of thickness, atmospheres, and for these quote-unquote secondary atmosphere compositions. So not hydrogen and helium dominated, but perhaps volcanically derived, a little bit like that of the Earth. And so when we see a flat line like this, there's kind of 3 major explanations. The first one being that this planet was a bare rock. And so what does this mean for the rest of the system? If we again play this game of trying to infer what a given planet's likelihood of atmosphere presence kind of propagates out to the other ones. The second thing is, can we compare this planet's atmosphere or the constraints that we have on its atmospheric composition to what we know about some of the solar system planets and their kind of template atmospheric signatures. And finally, again, taking a step back, this could be a completely different type of formation environment around a very different star than the sun. So we might expect very different compositions from what we're seeing on solar system terrestrials. So talking about the first thought experiment, if TRAPPIST-1d indeed is completely a bare rock, what does this mean for the rest of the system? What we did there was a modeling exercise where we start TRAPPIST-1d with different amounts of volatiles, different amounts of water. And at the beginning of its lifetime, it's very hot, and so a lot of the water can kind of be shielded in its interior and shielded from escape because it's dissolved in the rocky interior. But as the magma solidifies and more of the water is kind of pushed into the atmosphere and can escape to space, we're essentially wanting to figure out which of those initial planets ended up with even a sliver of an atmosphere. And that gives us a constraint on the amount of water that TRAPPIST-1d could have started out with and still ended up completely desiccated. What we learned there is very constraining, because one of the expectations of the TRAPPIST-1 system, because there are so many different rocky planets and they are very regularly spaced, is that they might have migrated from places in the system where there might be a lot of ices to begin with. But what we find is that if TRAPPIST-1d is desiccated, it means that the inner planets B and C, must have formed very dry, with less than 3 or 4 Earth oceans worth of water. Now, if we compare to the templates of solar system terrestrials, the second option that I mentioned earlier, we found that the signatures of methane for Titan, for an atmosphere like that of Titan, even accounting for the haze in Titan's atmosphere, isn't consistent with what we see on TRAPPIST-1d. Second, we also don't see the signatures of carbon dioxide and water that we would expect to see on an atmosphere like that of the Earth. But there are still some possibilities that remain. For instance, an atmosphere like that of Mars that would be extremely thin, so kind of be below our current detection limit, or an atmosphere like that of Venus, which would be, yes, very thick, but because it has these high altitude clouds, they essentially block the signatures from the atmosphere. And finally, we wanted to think about what would happen if TRAPPIST-1d instead actually had a water-rich atmosphere, but because it is in a very different rotation regime compared to the Earth that has one rotation every single day, TRAPPIST-1d is in this configuration, which is tidally locked, meaning that it has a permanent day side looking towards the star and a permanent night side looking away, kind of like the moon around the Earth. And so that might affect where clouds could form in its atmosphere. And because it's so close to the habitable zone, it's really not crazy to think that clouds can condense out of the upper atmosphere and perhaps alter our ability to detect water if present. And so this is the modeling exercise that we did. What you're seeing on the left is what we would see, so in orange is the features we would see in the transmission spectrum in the presence of a clear water-rich atmosphere. So this is clearly inconsistent with our non-detection of atmospheric features. But if we allow water to actually condense out into clouds in the atmosphere where it can, we get a map just like this. So this is kind of like a map of the Earth, but here you would be looking at the day side of the planet, and on the two sides, you're looking at the night side. So it kind of turns over like this. And what we're looking at when we're looking at a planetary transit is this rim between the two, what we call the terminator. That's really the region of the atmosphere that's absorbing the star's light from our line of sight. And what you can see in the shaded areas is that water clouds would actually form quite a bit in those regions, to the point that if we account for this cloud formation, because the planet is tidally locked and the clouds are at very different altitudes than where they are on Earth, we actually might also see a flat spectrum in that case. So we're kind of learning as we go which planets transmission spectroscopy can be really informative on, and for which of them we should have alternative strategies, like what we call emission spectroscopy, for instance, which I can talk about later if you have some questions. So in terms of the take-home messages from this study of TRAPPIST-1d, we figured out that even if the star is very tricky, it's a very active star with spots and bright regions at its surface that really complicate the analysis, we can reach this precision to probe atmospheres similar to that of the Earth. And so we're still left with those possibilities of whether TRAPPIST-1d is a bare rock, but then it would mean something very constraining about the formation of this inner system, which would have to be very dry. If it's similar to some of the solar system terrestrials, then it would have to have either a very thin atmosphere or a very cloudy one. And finally, we found that if it has a water-rich composition, because of its tidally locked configuration, we actually would not expect to see any atmospheric features because water clouds can readily form there. So that's kind of a broader lesson that we probably should apply to our searches for atmospheres more generally around these small stars, where it's much easier for planets to be locked in this tidal locking configuration, and clouds potentially blocking our view of even existing atmospheres. Now, moving on to the perhaps more exotic part of how we're thinking about habitability, perhaps more different compared to what you've been thinking about so far or hearing about so far, is thinking about exotic compositions, even on larger sub-Neptunes. So again, planets just a little shy of between maybe 2 and 4 times the size of the Earth, that would have very thick gas envelopes, but that maybe could still have liquid water. And there, this possibility would only be if you have a very thin hydrogen-dominated layer, so very different than that of the Earth, overlaying a layer of water that would essentially be heated up enough by the greenhouse effect from the hydrogen-rich layer to retain liquid water conditions. Now that we're thinking about sub-Neptunes, I need to break to you that we don't know their compositions at all, but like at the most basic level. We don't even know which of them have water and in what amount. And that matters a lot when we're thinking about potentially liquid water. The way that we interpret these planets' compositions at least the first order level is using what we call a mass radius diagram. So here you're looking at planet radius here as a function of planet mass. And you can plot where different planets lie. That gives you kind of their planetary density. And you can compare this with theoretical models of an Earth-like composition, where Earth and Venus are, for instance, or even a composition that's a bit, let's say, lighter rocks on average of 100% silicate compositions. But any planets that's above, that's larger than this 100% silicate line, essentially needs to have a volatile rich envelope just to explain how large it is given its low mass. So we think that all of these planets, the sub-Neptunes that I was mentioning, actually need to have an envelope. But the big uncertainty is that you can explain them very well with kind of person by mass hydrogen helium envelopes, just scaled down versions of a gas giant, or with tens of % of water, just kind of equally well. And the question is, so are these planets hydrogen rich, water rich, or just something in between? And so to break these degeneracies, what we need is atmosphere observations. The key that atmosphere observations can give us is through measuring the size of the molecular features that we detect in sub-Neptune spectra, like what we have here, for instance, for K218b, we can figure out how heavy on average the molecules in the atmosphere of that planet are. For instance, here, because the amplitude was very large, we can infer that, yes, we're seeing absorption from water, but it's water in a very hydrogen-rich environment, very much like this gas dwarf scenario. So while a planet like K218b might have a hydrogen-dominated atmosphere, the question is, what about the smaller sub-Neptunes that kind of bridge the gap between solar system kind of rocky compositions, and these larger planets that might just be smaller versions of the gas giants that are much larger. And so we had a large JWST program accepted to look at a handful of those planets, one of which is GJ98270. And what's really exciting about this planet, probably one of my favorite sub-Neptunes, is that it is the smallest of the sub-Neptunes for which we actually had an atmosphere detection. It's a very low density planet. It's only about 2 times the size of the Earth and 3 times its mass. So you can see that it's drastically larger than what you would expect for just a rocky planet of its mass. And it's at about 600 Kelvin, meaning that if it had any water present, it would be in the atmosphere or kind of in a fluid state in the envelope, but it wouldn't be in the liquid state. Still, we wanted to learn whether there was a difference between the atmospheric water content of a larger sub-Neptune like K218b and a much smaller sub-Neptune like GJ98270. And so for this reason, we observed 2 transits of GJ98270 with JWST, this time with the nearest source instrument. And there, what we found was instead very small water features, as you can see here, that are very visible all throughout the near infrared. And what this turns into, if you go into interpretation land, is that the atmosphere has to be extremely rich in water. It has to be made of at least tens of % of water. And we know that even if water wasn't the dominant component, hydrogen wouldn't be. It would be another one of these very heavy species, which could be, for instance, carbon dioxide, which we didn't have access to with this restricted wavelength range. So now we're observing it at longer wavelength where we could see whether some carbon species are hiding there as well. Or it could be other things like methane, for instance. Another hint that also goes into that direction of a not hydrogen-dominated sub-Neptune atmosphere is the non-detection of atmospheric escape. So you can think of it this way. Hydrogen and helium are extremely light atmospheric elements. And so on a planet that has a very low density, that doesn't have a very deep gravitational potential well, and that's also relatively highly irradiated, you would expect to see some sort of cloud of hydrogen and helium continually escaping from this planet's upper atmosphere. This was a key prediction specifically for GJ98270 because it's so small and so low density that really a hydrogen-helium envelope is barely stable. But instead, in our observations, as you can see at this dashed red line is where you should see a huge absorption signature if there was helium escaping. And there have been other searches for hydrogen escape that also haven't been conclusive. And this can be explained if the atmosphere isn't dominated by hydrogen and helium. If, for instance, it's dominated by water, even if water is made of hydrogen and oxygen, and so some hydrogen could actually escape, the metal-rich nature of the atmosphere will actually make the outflow much more ionized, which will make it much harder to detect. If we use Lyman alpha, for instance, to try and detect hydrogen escape, then we're just sensitive to neutral hydrogen. So that would explain why on this specific planet we have a non-detection of atmospheric escape, because again, in line with what we see in the lower part of the atmosphere, that seems to have a high metallistic composition. And finally, now if we think about this at the population level, I superimposed 3 spectra of a larger planet, K218b, 2.6 Earth radii, much less irradiated, much colder. Then a bit hotter planet, TI270d, with about 350 Kelvin. It's a little bit hotter, but also a little bit smaller. And you can see there that the atmospheric features have shrunk. And there, GJ98270 at the very bottom, that's the most irradiated of the 3, and also the smallest one. And we seem to have, again, if we look in this mass radius space, this kind of gradient in metallicity towards what we call the radius valley, which is the dearth of planets between the super Earth and the sub-Neptunes. If you remember, this kind of 2 peaks distribution that I showed at the beginning, which suggests that there might be something very fundamental happening here, that perhaps these planets, because they're more irradiated, essentially have gradually more metal enrichment, or it could also be that the planets that actually can survive, even at high radiation levels, are the ones that formed with a lot of water. So we're really starting to gather these hints that inform us on the distribution of water across planetary systems that's really essential for the search for life. So in terms of wrapping up this section on GJ927d, we found for the first time an archetype planet that doesn't have a hydrogen-dominated envelope and instead has a very strong water absorption features. And it seems that more broadly at the population level, sub-Neptunes seem to have their atmospheric features shaped by gradual metal enrichment, although there's probably more diversity going on with perhaps some trends in even the types of aerosols or clouds or hazes that could be forming. But already we're starting to gather these hints that really weren't accessible at all in the pre-JWST era. And so finally, where I'd like to end is how we can connect this new understanding of the atmospheres of sub-Neptunes to their bulk compositions and essentially to their interiors. So if we take a step back again, if we know the mass and size of a planet, of a given sub-Neptune, we can explain it with a hydrogen-dominated envelope. But we could also explain it with a water-dominated envelope by kind of changing the ratio of core to envelope in terms of how the mass is distributed, which is what I mentioned in the previous part of this talk. Now, if you also change the composition of the core, you're adding in another range of uncertainty where you could have different amounts of iron or silicates that we really don't have access to. And finally, again, because what we're looking at with JWST is really a very upper region of the atmosphere, we need to understand how what we're seeing in that upper atmosphere actually relates to the bulk. Because there could be, like there is on Uranus or Neptune, for instance, these metallicity gradients, where you think you're seeing a low metallicity atmosphere, but actually in the deep envelope, it's extremely metal rich. And you could say, okay, we're seeing already all these species in the upper atmosphere. Why do we care so much about what the bulk composition is, what the composition of kind of the entire underlying planet is? And there are quite a few reasons why we actually care a lot in terms of our broader understanding of exoplanets. The first one being planet formation. What we're seeing at the top of the atmosphere doesn't tell us a lot yet about the formation building blocks. What we care about is how much ice was involved in the formation, how much silicates was involved, kind of what were these, the relative masses of these ingredients that formed together, that merged together to essentially form the planet that we're seeing today. And so if we don't have a way to link what we're actually measuring in the atmosphere to the interior, then it's very hard to make links to predictions from competing formation scenarios. The other thing that's really interesting is that because they could have these hydrogen-rich envelopes, sub-Neptunes could heat up their interiors enough that the rocky surface is actually not solid, but instead molten. And what that can give rise to is a lot of chemical interactions between the overlying gas of the envelope and the underlying magma. And so we think that the presence of a magma ocean could actually alter quite drastically the atmospheric composition. So that matters for the interpretation of what we see in the upper atmosphere. And finally, as I also mentioned or hinted at earlier in this talk, there could be these planets that are what we call Hycean worlds. So sub-Neptune, so much larger than the Earth, that would still have hydrogen in their atmospheres, but that would be overlaying a layer of liquid water. So that's interesting in the context of, did we measure a hydrogen-dominated envelope, but actually could the planet still have some features that still make it interesting from a habitability perspective? And so I'm not seeing my slide. Give me 1 second. Yeah, so the question that remains here is, for which sub-Neptunes could we learn about their interior from their atmosphere? Because this is, as I said, such an important question. And so there, and for the remainder of this talk, we're going to look at a few water phase diagrams. So what you're looking at here is pressure as a function of temperature here. And the way to think about this is as you're higher up in the atmosphere of the planet, you're going to be higher up on this plot. And as you get deeper and deeper towards the interior, essentially, it's going to get progressively higher pressure and hotter. And what really matters is whether at the base of the hydrogen layer, the temperature is suitable or not for the presence of liquid water. For very cold planets, actually, yes. If you have a planet that has an atmosphere temperature of about 200 or 250 Kelvin, then at the base of this hydrogen layer, you could end up in a state where water is in the liquid state. So you would have these high CN compositions. But actually, for the much more numerous sub-Neptunes that we know about, they're a little bit warmer, that are maybe 300, 400, 500 and more Kelvin. At the bottom of this hydrogen layer, water would instead be in what we call the supercritical state, which is a fluid state where it is highly miscible with things like hydrogen. And why this is interesting, even if less interesting perhaps because it can't be liquid water, but is very interesting from the perspective of linking atmospheres to interiors, is that if water can be in this supercritical state, then it means that you could have this well-mixed composition where what you see in the upper atmosphere is actually representative of your bulk envelope. And so that enables you to really constrain a whole range of the volume, a whole fraction of the volume of your planet just by studying the upper atmosphere. And so now if we combine with what I mentioned before, for those warm sub-Neptunes, we could have chemical interactions with the interior via, for instance, a magma ocean, which could inform us on the composition of the rocky mantle. And those would be impacting an atmosphere that's well mixed all the way to the upper part, which we're probing with JWST. And so right now, what we're trying to figure out is how we can use this enhanced understanding of how to link interiors and atmospheres to decipher the role of both formation and chemical evolution with interactions between the atmosphere and the interior via our measurements of metallicity and chemistry. And so one of the efforts in that direction is the development of new codes that can use the information from atmosphere transmission spectra and translate them into an increased understanding of what's going on in the interior. And so I'd like to end on one note on my latest work, actually figuring out whether we can make this assumption of what we see in the atmosphere is really representative of the interior for all or most warm sub-Neptunes. And this is considering the fact that actually I made a little simplification when I said that water and hydrogen are well mixed when water is in the supercritical state. There is what we call this critical curve that separates places where water and hydrogen would indeed be very well mixed, even at in these deep regions, from colder compositions where even if you're in the supercritical regime, you would have these compositional gradients because their water and hydrogen actually can't coexist in a single phase, even if this isn't like a phase transition, like water to liquid to vapor, etc. And so actually, if we map this out in the mass radius diagram, which I've done here, showing these different lines just show where planets with different envelope mass fractions would lie. We can see that this doesn't happen if you have a solar metallicity hydrogen-dominated atmosphere. Otherwise, you would have thicker lines going on here. But as you increase the atmospheric metallicity to 100 and 200 times solar, very similar to what we're actually finding on sub-Neptunes, throughout a lot of your mass radius space, if not all of it, for planets that have temperatures between 300 and 500 Kelvin, so similar to a planet like TY 270d, one of the ones that I mentioned earlier, you have this window where your metal-rich sub-Neptunes would actually have their upper atmospheres very depleted in water compared to what the envelope really contains. And so this is really just another piece of the puzzle, figuring out at which temperatures we should be looking for those atmospheres where we can learn the most from their interiors by looking at their atmospheres. So I'll leave here my take-home messages to wrap up. But yeah, we're learning about small planet atmospheres and figuring out which small rocky planets on temperate conditions could have atmospheres. TRAPPIST-1G is one example of that. For GJ-9270, it was the first time that we discovered a sub-Neptune atmosphere that was actually not dominated by hydrogen and helium. So that really changes our perspective of the distribution of water in planetary systems. And we're starting to understand for which of these planets we can really connect what we see in the upper atmosphere to their bulk composition with links to their formation. Thank you. And I'll take any questions, of course. Just so you know, you're muted. So if you're saying something in the room, I cannot hear it.
Thank you. Yeah, no, we are taking questions now. Maybe I'll ask one to get things started. If you could take us back to one of your water phase diagrams, talking about supercriticality and
About what, sorry?
yeah, so basically how one can form these miscible supercritical envelopes. The question I have is, but whether water is in a supercritical state or not, of course, also depends on the pressure. But are we imagining a scenario where the miscible state goes all the way to the exosphere? Wouldn't the
Yeah, okay, so there are different mixing processes, I would say. If you're really in the supercritical state, you can assume that potentially you're in a state where the atmosphere is convective. Even in the deeper atmosphere, the atmosphere is going to be convective. So you're going to have mixing that happens this way, that enables you to have a certain region of the atmosphere with relatively consistent composition. Afterwards, the assumption that it goes all the way to the upper atmosphere is saying that even in the radiative part of the atmosphere, because we have strong evidence of vertical mixing perhaps through winds in sub-Neptune envelopes that comes from 3D atmosphere modeling, tells us that it's really not that hard to, like, if your main composition is water and hydrogen, there isn't a lot of phase separation that should happen in the upper atmosphere, because water will really be stable, even in chemical equilibrium, will really be stable all throughout. So I would say in the lower part of the envelope, in the supercritical state, then you could say that you would just have mixing there. But then even in the vapor state, if you're in a convective regime, then that would be how the mixing happens. And in the radiative part of the atmosphere, that's more relying on even chemical equilibrium calculations that don't predict huge variations in the amount of water you should see all throughout the atmosphere, assuming a consistent kind of oxygen budget.
Great, thanks. Other questions?
There's one in the chat.
Okay, can you read that?
I don't
I'm not seeing it.
Yeah, can you see a question in the chat? I guess.
Maybe if I stop my. Oh, okay, no, I can see it. What's your opinion on hot Jupiter migration? I think the evidence for hot Jupiter migration is one that is probably going to come more strongly from studies that rely on dynamics than only the atmospheric composition. I think one of the main takeaways that we've had of the studies of hot Jupiters is that they're really kind of testing the limits of our models and whether we can really link, again, this is a different way of doing this, but whether we can link the elemental abundances of like oxygen, carbon, sulfur in the upper atmospheres of these planets, really pin them down to where they formed. That's a really tricky thing to do because there could be a lot of atmospheric evolution going on. So I would say that for hot Jupiter migration, probably the strongest evidence comes from studies of planetary multiplicity or planetary dynamics, and essentially seeing if there is evidence for this late migration in the final architectures of the system, because having a Jupiter mass planet migrate in is going to really disrupt your entire planetary system. And so if we find that the occurrence rates of, for instance, kind of small close-in exoplanets also match in those systems where you do see hot Jupiters, also match being disrupted or not being disrupted by a giant planet migrating, I think that's probably the strongest bet so far. I think theory right now hasn't caught up in the way of leveraging the very exquisite atmosphere information we get for those hot Jupiters compared to much smaller planets like the ones I was discussing, and really linking that to formation, because they can really be impacted, like what you see in the upper atmosphere can really be impacted a lot by your atmospheric dynamics or even sequestering of some of those elements in the interior. So I think the jury's still out, but there is definitely evidence that some hot Jupiter systems are consistent with a late stage migration. Could it be that some hot Jupiters have large iron cores versus others not? I'm not the right expert to really speculate on that. I think we don't have the mass and radius information that we have is still quite degenerate in terms of core compositions in particular. But one hint could come from studying the abundances and the metallicities, which has been done also of the host stars that seem to host hot Jupiters preferentially, to see if that could enable more easily in situ formation. But yeah, that's not my area of expertise.
Maybe I can bring this closer to your talk. So if you see sub-Neptunian objects, and you could actually measure the atmosphere's density masses very well, is there a way to discern whether they were formed where you see them, like in the habitable zone of the star, or if they migrated inward?
Yeah, so I would say that in recent years, this picture has really become a lot more complicated because specifically of this idea of magma-ocean atmosphere interactions. Before, the idea that was that you couldn't have substantial amounts of water in the atmosphere of a sub-Neptune if it hadn't formed in a region of the planetary system where there was a lot of ices. So for instance, it formed beyond the ice line and later migrated inwards, and so a lot of water got released into the atmosphere where you're seeing it today. But now there is a new understanding that even if the planet formed with a hydrogen-dominated envelope, this hydrogen interacting and essentially melting into the magma could interact with the oxygen contained in like MgSiO3 or so silicate rocks or iron oxides, and essentially form water and release water into the atmosphere. And models actually predict that you could release into the atmosphere like tens of percent by volume of water. And so now this really kind of blurs our understanding of, okay, if I'm seeing a water-rich atmosphere, what does that mean about formation? And that's where I think it becomes really interesting to think about chemistry more broadly than just water or no water or amount of water. We really need to look at the chemistry of different elements like carbon, sulfur, and because those will have different ratios and different signatures, whether they are impacted by ongoing interactions with the interior, which would release, for instance, a lot of oxygen into your atmosphere. So you might expect maybe more CO2 than CO perhaps, or you might expect to be able to see sulfur dioxide that's released from the interior because of the sulfur that's released from the interior. But water alone, now we figured out, is really not going to be enough to tell us where a planet formed. We really start to go from individual molecules to a whole chemical inventory.
Very interesting. Any last question? Okay, great. Yeah, that was very, very interesting. Thank you so much.
Thank you.